Meet Alex, our intrepid explorer standing at a fork in the road, map in one hand and a compass that's mysteriously broken in the other. To the left lies the winding path of spam filtering, littered with deceptive traps. Ahead, the gleaming towers of stock forecasting, where fortunes ride on razor-thin margins. And to the right, the vertigo-inducing skies of autonomous drones, where one misstep sends your robot plummeting. Which path should Alex choose first? And more importantly, how can you guide the way? Today, you'll don the mentor's cloak, navigating every twist, outsmarting every trap, and mastering the AI tools that turn raw data into decisive action. Forget magical incantations. AI is pure craft, algorithms and models chiseled to mimic facets of human thought. Machine learning is your Swiss Army knife for spotting patterns in mountains of data. Deep learning is the high security vault of multi layered neural networks, unlocking subtleties hidden in high dimensions. Under this canopy, NLP turns every tweet, email, or legal brief into numbers. Computer vision sees the world in pixel perfect detail. Reinforcement learning trains your AI athlete through wins and losses. Generative models spin fresh text, images, or music from what they've learned. Think of AI as a troupe. Each specialist brings its unique flair to the grand performance. Every hero needs a clear quest. Vague goals like make predictions are headless dragons. You'll swing and miss. Instead, sharpen your target. Spam filter, catch 95% of phishing messages with under 5% false alarms. Stock predictor, forecast next day returns within plus or minus 2% error on the S&P 500. Drone navigator, maintain a 2-meter safety buffer at 20 kilometers per hour. This precision shapes your data, model choice, and success criteria. Alex learned that fuzzy goals lead to wasted GPU hours. Yours will be crystal clear. Alex discovered 4 enchanted trails through the sprawling realm of AI, and each path holds its own magic and challenges. Supervised learning. Picture a lantern lighting the way. Here, every data point comes with a label, a clear answer guidebook at your side. You feed your model examples of spam and not spam, of cats and dogs, of fraudulent transactions and legitimate ones. Algorithms like logistic regression, random forests, or convolutional neural networks learn directly from these labeled signposts. The result? High accuracy and fast convergence whenever your ground truth is reliable and plentiful. Unsupervised. Learning. Now step beneath the moonlit canopy where no labels exist and the terrain is unknown. Your compass here is structure itself. You let algorithms like k-means clustering, principal component analysis, or autoencoders reveal hidden tribes of data points and unveil the valley of latent features. This path is ideal for exploratory adventures, discovering customer segments, detecting novel anomalies, or visualizing complex datasets in 2 dimensions. Semi-supervised. Learning. Sometimes you have only a handful of labeled waypoints, but mountains of uncharted data. In this hybrid realm, you carry both map and compass. Techniques such as pseudo-labeling let your model assign pseudo-labels to confident predictions, while consistency regularization ensures that small tweaks in input don't sway its verdict. Alex found that with just 10% of the data labeled, his model reached over 90% of the accuracy of a fully supervised approach, slashing annotation costs and scaling performance. Reinforcement learning. Finally, imagine a grand tournament arena. Your AI agent takes an action, receives a reward or a penalty, and learns which moves bring glory. Classic Q-learning and deep Q networks tabulate and approximate the value of every state action pair, while policy gradient and actor-critic methods directly refine the strategy itself. This trail suits dynamic sequential challenges, robotic navigation, strategic gameplay, or even adaptive portfolio management, but beware the need for massive simulations and well-crafted reward signals to avoid shortcuts or reward hacking. Hovering above and weaving through all these paths is generative modeling, the ultimate artisan. Whether through GANs dueling in creative combat, variational autoencoders bending data into smooth latent spaces, or large language models conjuring text from vast corpora, generative techniques draw strength from each learning paradigm to craft entirely new worlds of data and possibility. In the well-lit classroom of supervised learning, every example arrives with its own answer key. Your model studies each example much like a student poring over flashcards, always knowing whether it's a spam or ham, fraudulent or legitimate. Let's dive deeper into the key techniques. Logistic regression. Think of logistic regression as a swift courier delivering binary verdicts. It draws a simple boundary, a straight line or hyperplane, that separates one class from another. Behind the scenes, it estimates the probability that an input belongs to the positive class, making it perfect for rapid, interpretable decisions like email filtering or credit approvals. Random forests and gradient boosting. These ensemble methods act like a council of wise tree elders. Random forests grow hundreds of decision trees on random subsets of data and features, then aggregate their votes to tame noisy, complex datasets. Gradient boosting, on the other hand, builds trees sequentially. Each new tree corrects the errors of its predecessors, honing in on hard-to-predict examples. Together, they strike a powerful balance between flexibility and robustness, often winning tabular data competitions. Convolutional neural networks, CNNs. Imagine sending a platoon of image scouts to scan local regions for edges, textures, and simple patterns. CNNs do just that. Convolutional filters slide across an image, detecting low-level features before combining them into higher-order concepts like shapes or objects. This hierarchical learning makes CNNs the undisputed champions of image classification, object detection, and any task where spatial context matters transformers. While CNNs excel at local pattern recognition, vision transformers act as vigilant overseers, capturing global relationships across the entire image through attention mechanisms. They break the image into patches, like pages in a book, and learn which patches deserve more focus, modeling long-range dependencies that help in fine-grained recognition or when context from distant regions is crucial. When your data is clean, plentiful, and accurately labeled, these supervised methods become your most reliable allies, delivering rapid training, high accuracy, and in many cases, built-in interpretability. With them in your toolkit, you can tackle everything from binary classification to multi-class recognition with confidence and precision. When Alex ventured into the wild frontier of unlabeled data, unsupervised methods became his trusty compass, revealing hidden patterns and guiding each next step. K-means. Clustering. Imagine gathering villagers by their shared traits, age, preferences, or spending habits, and watching them naturally form communities. K-means does exactly that. It partitions your data into K-coherent tribes based on similarity. For marketers, this means uncovering distinct customer segments. For network security, it can reveal clusters of normal traffic versus suspicious outliers. Each cluster becomes a new hypothesis to test or a target for tailored strategies. PCA and TS&E picture a treasure map that flattens mountains and valleys into a two-dimensional color-coded landscape. Principal component analysis, PCA, reduces dimensions by capturing the directions of greatest variance, your broad contours, while T-distributed stochastic neighbor embedding, TS&E, preserves local neighborhoods, highlighting subtle relationships in a fog of features. Together, they turn your high-dimensional data mountain into an intuitive 2D plot where clusters, gradients, and anomalies leap off the page. During compression, they distill the essence of each example. During reconstruction, any large discrepancy signals something unusual. In practice, autoencoders excel at anomaly detection, flagging defective products in manufacturing or spotting fraud in finance whenever the reconstruction error spikes. Indeed, Alex first applied k-means to group user behavior on his platform, uncovering three distinct personas. Next, PCA revealed that two features, session length and click depth, accounted for 80% of variance, guiding him to focus on UX improvements. Finally, an autoencoder trained on normal traffic quickly flagged novel attack patterns in real time. By combining these unsupervised tools, you can rapidly survey the terrain, formulate hypotheses, and engineer features that supercharge your next supervised model. Labeling data can feel like mapping an entire continent by hand, but semi-supervised learning hands your model the quill. With just a few signposts, it charts the rest of the terrain on its own. Pseudo-labeling. Imagine your AI as an apprentice cartographer. You show it a handful of labeled samples, say 100 images of cats and dogs, and then it ventures into the unlabeled wilds, assigning its best guesses as pseudo-labels. As long as you filter for high-confidence predictions, the model's self-generated labels become new training data, multiplying your effective dataset without extra annotation effort. Over successive training rounds, the model refines its own map, correcting earlier mistakes and expanding its knowledge frontier. Consistency, regularization. But what if a tiny shift, a slight rotation of an image, a small synonym swap in text flips your model's decision? Consistency regularization enforces stability. It penalizes the model whenever minor perturbations of the same input produce divergent outputs. By demanding that close inputs yield close predictions, you smooth the decision boundary and improve robustness to noise, data drift, and adversarial tweaks. In one of Alex's experiments, only 10% of the dataset was manually labeled. He then applied pseudo-labeling to bootstrap the remaining 90%, while consistency regularization kept the model from overfitting on its own guesses. The result? 90% of the accuracy of a fully supervised model, achieved with a fraction of the cost and time. By blending human guidance with machine-driven annotation, semi-supervised methods let you stretch scarce labels into a rich training resource, unlocking high performance even when expert labeling budgets run dry. Imagine Alex's AI as a curious creature in a vast sandbox, constantly experimenting to discover which actions lead to treasure and which lead to traps. Two core strategies guide its evolution: Q-learning and deep Q networks, DQN. At its heart, Q-learning builds a giant lookup table, estimating the long-term quality Q value of taking action A in state S. But real-world problems have too many states for a table. That's where deep Q networks step in. A neural network approximates the Q function, learning to predict expected rewards from raw inputs like pixels or sensor readings. Over thousands of simulated trials, the network updates its weights whenever its predicted Q values diverge from actual returns, gradually mastering which moves pay off best. Actor-critic methods. Think of this as a coach-player duo. The actor proposes a policy. In this state, choose action X with probability P. The critic evaluates that policy by estimating the value of the current state or state-action pair, signaling whether the actor's choice was wise. As the actor experiments, the critic provides feedback to nudge the policy toward higher rewards. This two-pronged approach often converges faster and handles continuous action spaces more gracefully than Q-learning alone. When to use RL. Robotics. Teach a robot arm to grasp objects by rewarding stable grasps and penalizing drops. Game AI. Train agents to outmaneuver opponents in simulation before facing human players. Drone navigation, reward. Smooth, collision-free flight paths through cluttered environments. If the reward function isn't airtight, your agent may exploit loopholes, spinning in circles to rack up points, for example, instead of completing the intended task. Moreover, large state spaces and high-fidelity simulators can burn through GPUs and days of training. So, begin with a simplified environment, like grid worlds or low-dimensional simulators, so your AI learns the fundamentals without overwhelming compute. Once basic skills are mastered, scale up complexity and refine your reward design to avoid unintended shortcuts. Step into the AI atelier, where generative models are the master artisans, each with its own style and superpower. Generative adversarial networks, GANs. Imagine two artists locked in a friendly duel. The generator dreams up images, say portraits or landscapes, while the discriminator critiques each piece, asking real or fake. With every round, the generator learns to produce ever more convincing art, and the discriminator sharpens its eye. This adversarial tug-of-war continues until the generator's creations are indistinguishable from genuine samples, whether that's photorealistic faces, artwork in the style of Van Gogh, or entirely novel designs. Variational autoencoders, VAEs. Think of VAEs as sculptors working in a pliable medium. They learn to compress data, images, sounds, or text into a smooth, latent space where neighboring points represent similar concepts. You can then sculpt by moving through this space, blend one face into another, interpolate between handwriting styles, or generate new chemical structures for drug discovery. The result is a continuous world of possibilities where you can navigate seamlessly from one idea to the next. Large language models, LLMs, e.g., GPT style, these are the poets and storytellers of AI. Trained on vast oceans of text, they learn patterns of grammar, style, and fact. Prompt them with a title, a question, or even half a sentence, and they'll spin out coherent paragraphs, craft code snippets, or compose poetry that resonates emotionally. From drafting emails to brainstorming product names, LLMs have become indispensable creative partners. Generative models aren't just for art, they're your R&D dream team, for example. Data augmentation, synthesize rare classes, e.g., medical X-rays of uncommon conditions, to balance data sets. Simulation, generate realistic scenarios, traffic patterns for autonomous vehicles, or varied customer interactions for chatbots. Rapid prototyping, mock-up UI designs, marketing copy, or concept art in seconds, accelerating your creative workflow. In the hands of a skilled creator, generative AI transforms raw imagination into tangible assets, fueling innovation across art, science, and industry. Imagine you're tasked with protecting millions of shoppers at the point of sale, building a real-time credit card fraud detector that must flag illicit transactions before they're authorized. Here's how you choose the right AI champion. Frame the quest. First, define your objective with laser focus. Catch at least 95% of fraud, yet keep false alarms below 1%. You have a historical trove of 10 million transactions. Only 0.2% are fraudulent, featuring amounts, merchant codes, timestamps, locations, and device fingerprints. And in deployment, you face two ironclad constraints. Every prediction must land in under 50 milliseconds on a CPU, and regulators demand a clear explanation for every declined charge. Audit your 4 criteria. Data. You possess massive volume but extreme class imbalance and mixed feature types, some missing values. You need algorithms that tolerate noise and sparse positives. Interpretability. Transparency is non-negotiable. Any declined transaction must be defensible to both customers and auditors. Compute. With no GPUs and sub-50 millisecond budgets, your model must train and infer cheaply on commodity hardware. Latency. Real time at the terminal means every microsecond counts. Batch jobs won't cut it. Shortlist the contenders. 3 weapons emerge. 1. Logistic regression with engineered interactions and semote. 2. Gradient boosted trees, XGBoost light GBM for imbalance robustness. 3. A small neural network for potential nonlinear nuance. Score the matrix. We rate each on data, interpretability, compute, and latency from 1 to 5. Logistic regression scores high on interpretability, compute efficiency, and latency, with moderate data needs totaling 19 points. GBTs earn a 17 thanks to data handling and decent speed. The small NN, hampered by opacity and heavier inference, reaches only 11 feet. Declare the champion. Logistic regression wins. It balances your data constraints, offers full transparency, runs in microseconds on CPU, and meets your fraud catch targets. You prototype it with L2 regularization and interaction features. Validate on holdout data, then monitor live performance. If rare fraud patterns slip through, you can always introduce gradient-boosted trees as a second-stage sieve. By systematically auditing your data, transparency needs, resource limits, and speed requirements, and scoring each model, you turn guesswork into a data-driven decision. That's how Alex would conquer the AI Crossroads, and how you'll choose your champion for real-time fraud detection.